My workshop is full of screw threads. All these cabinets, they just have lots of nuts and bolts in, all little drawers. And there are more over here. What's this one? Brass nuts and bolts. Oh yes, some extra large ones here. Bit of 20mm studding, for instance. But that's not all. There's a sort of overspill area here. God, more than a lifetime supply of bolts there. I think they came from Rex's workshop. But it's not just nuts and bolts. A lot of the tools have screw threads on, so G-clamps just depend on screw threads. Then the largest screw thread I've got in the workshop, I think, is on my metal folder. Sort of brings down the top to clamp the metal in place, ready for bending. So screw thread there, and of course there's an obvious screw thread on my lathe, the lead screw. In most of the tools do have screw threads, but they're hidden, sort of kind of protect them. So like on the mill, you can see the one for the horizontal travel is under there. So there are screw threads all over my workshop. Lots and lots of them. This video is my experience of using screw threads over the years. The first part is sort of just the basic ideas about them. The second part, there's a series of examples of screw threads I've used in my machines, and some successes and some disasters. The video is quite long, so here's the contents list, so you can skip forward if you want to. So I'm going to start by looking at how threads are made. Well, when I want to make a thread, I almost always use a thing called a tap, or its companion, a die. So this is a tap, looks a bit like a bolt, but it's got these flutes cut out of it, and it's made of a very, very hard steel that when you drive it through a slightly undersized hole, it literally cuts the thread as it goes. And a die is the same thing really, but looking a bit like a nut, but with bits cut out, and this will drive its way over a shaft, forming a thread in the same way. So I thought I'd demonstrate this by cutting a thread in a bit of 6mm 1/4 inch steel. So first of all, you have to drill the undersized hole. For a 6mm thread, it's a 5mm hole. So normally what you would do is to hold the tap in a tap holder. This is a traditional tool, and then form it by hand. But I have to admit, I don't often use it. I nearly always use a battery drill or the drill press instead. So I just tighten it up as if it was a drill bit. Put it on the screwdriver setting, and with not too much torque, because you don't want to break the tap, and then a little bit of lubrication on the tap, right, and then you just sort of have to go for it. And I often find it works better actually at the high speed. Well, made a bit of a meal of that, but it does fit the bolt very nicely. Now the one drawback of this, it's not completely at right angles to the bit of steel. It's hard to judge just doing it with a battery drill. So this is why I often use the pillar drill instead. So really it's exactly the same thing, except that I mount the tap in the pillar drill, and the pillar drill has belt drive, so that's a bit like the adjustable torque in the battery drill. Doesn't have to, it'll just stop if there's too much torque. A couple of things I've found useful. I used to find that taps didn't last very long. Perhaps it's the way I use them. But a few years ago I started using slightly more expensive ones. They're got yellow rings on. It's a sort of standard, the yellow ring. They cost about £9 each. So, but they do seem extremely sharp and to last a lot longer. I sometimes feel they really just cut steel like butter. The other thing I found useful about tapping, this is really for very tiny holes for 2mm and 2.5. I don't know if they're yellow ring, but I just have buy a pack of 10 from China. They're so fragile, they do break quite often. But what I've found helps them to break a bit less frequently is to drill the holes a little bit bigger than you're supposed to. So 1.6mm is the approved size for a 2mm tap, but I drill a 1.7mm hole, which is what I've drilled through here, and it just does slide through quite a lot more easily, and as far as I can see it still has plenty of strength. I've never really had any problems with it. So a die fits into a die holder, get the right way around, and in a way this is even harder to get it at right angles to a bit of bar as you twist it round. Some die holders have collars on to sort of guide them. That's very helpful, but mine doesn't. So what I end up doing, I nearly always, if I want to put a thread on the end of a shaft, I do it in the lathe. So I put the bar in the chuck of the lathe. Now the thread goes in this die holder, but it's made specially for a lathe. So you can see it goes in there. Have to tighten up the Allen keys. And this fits in the tailstock of the lathe, like that. So now put a bit of oil on it, lubricate it, set the speed. You don't want to go around too fast. Oh, it's actually on the right speed, about 70 RPM. And it'll literally wind itself on to the end of the bar. The sharp teeth of the dies kind of dig in. And that's all there is to it. Just got to unwind it again. And there it is, a pretty perfect thread. So I've got a bit of bar in the lathe, and this is my cutting tool. And as the bar rotates, the tool post will move slowly down the bed of the lathe, creating the thread with any luck. So the tool post is moved along the bed of the lathe by this rotating lead screw. Then in the head of the lathe there's a gearbox down the bottom which adjusts the speed of the lead screw, so you can set it for any different pitch, in this case both metric and imperial threads. Well, I don't often make threads like this. I find they tend to turn out all rough and not very good. I do some fine cycle threads occasionally. Today, a totally different way of making threads has become widespread. The two plates have rows of sharp ridges. They also taper a bit towards the front, so they trap the bar in the gap and press the thread into it as they roll through. Every method of cutting a screw thread involves an existing screw thread. So obviously with a tap, the tap itself is a screw thread. With the lathe, the thread is on the lead screw. Not so obvious with thread rolling machines, but they still do involve screw threads. So if you take the example of the lathe, the lead screw, the machine that cut this lead screw almost certainly cut the lead screws for many other Colchester lathes. And then the machine that cut those lead screws cut the lead screws for a lot of other manufacturers' lathes. So there's a sort of family tree of screw threads that in a theory ought to go back to one original screw thread. Of course, it's not as neat as that. The earliest known screw thread is on an olive press made entirely out of wood, and I don't think that originated any other screw threads. But at the beginning of the Industrial Revolution, before there were strong metalworking lathes, there was a vogue for making screw originating machines, and the most famous one in Britain was made by Henry Maudsley. It's in the Science Museum. I've been to see it, but it's completely baffling. I have no idea how it works. It's all underneath the working bits, I think. But there's a helpful diagram I found, so this is what I've based my own version on. But it's much more fiddly and difficult than I was expecting. So to start with, I made a curved blade out of tool steel, well, out of spring steel. With a sharp edge. Now that goes in here, and I've mounted it at a slight angle. I'll just turn this round. It doesn't look very much from there, but it is slightly angled outwards at the top. I will now put a bit of aluminium, a softer metal, into the vise, and now tighten up the curved knife against the, that's probably about right. And now I just have to start turning the bar, and with a bit of luck it will start to form a spiral. I can see it's doing it quite well now. But Maudsley actually went a bit further than that. So on the other end, if I turn this round, I've mounted an actual cutting tool in here. So the idea is that as the rod spirals its way through the tube, that this cutting tool will cut a proper cut, unlike the shallow knife mark on the other side. See how that works now. I think that needs to be, that's looking good. I may have gone a bit too far with that, I don't know. You can see the swarf coming off the cut, but you can't see the thread it's cutting because it's disappearing inside the tube. Well, I think I'll leave it there. If I remove the bar, you can now see my final rather imperfect thread. So there we have it. That's the knife blade cut that was pulling the rod through, and that's the actual cut made by the cutting tool that is a lot neater and will be the beginnings of an actual thread. And the clever thing about this is that you can actually make a thread that's more accurate than the one you started off with, because if you clamp something over a number of threads and use that to move the next bar through when you're cutting the next thread, it kind of averages out the imperfections in the individual threads. So by the beginning of the 19th century, people did have accurate threads and nuts and bolts, but each manufacturer made their own, and none of them were interchangeable. Then one of Maudslay's apprentices, Joseph Whitworth, took it on himself to standardise everything, and he bought nuts and bolts from a variety of different manufacturers, and he decided his standard was the best, and here it is. It stood the test of time extraordinarily well. At the time it was used on the very first cameras as the thread that fixes them to tripods. So this is an ancient camera I've got. That's the base. So it was still being used in the 30s and 40s. But here's my digital camera. Still got the thread on the bottom for fixing to a tripod, and it's still exactly the same original Whitworth thread. Well, although Whitworth's standard was a brilliant idea, other people quickly brought in other standards, so it soon became quite messy and complicated. So today there are lots of different standards. The main difference between these threads is that some are very coarse and some are very fine. Whitworth's was a coarse thread, more like this, and metric is somewhere in the middle. And in America, still today, you get a coarse thread and a fine thread, but in Europe people generally just use the metric standard, though it's actually called the metric coarse, and there is a finer thread. Finer threads are supposed to be stronger because they cut into the bolt less, I think, but they jam up more easily and they can rust up, and also it's just more fragile, the thread, so it can get damaged. So in a way the metric is quite a good compromise. I used to think that bolts were made by starting off with a bar that was the diameter of the head and then turning the rest of it down till it reached the right diameter to the thread. But it's actually much more fun than that. And I don't know if it'll come off. No, it's got a bit jammed, which it does. Turn it upside down. Whoops. Tap it out. In fact, when they make bolt heads, they usually stamp them once to get their general shape, and then a second time with a shaped punch to get the hex shape and also any text you want to have on the head of the bolt. So beside the different standards, of course all bolts come in different lengths. I always have a few long ones because it's very easy to chop them down, which I do with the angle grinder. When they come out of the angle grinder, the edges are quite sharp. You can't always get a nut over them. So then I take them to the linisher. They come out of the linisher looking like this, and then of course it's very easy to get a nut on. A quicker method is to put a nut on before grinding. Then when you take it off, it restores the end of the thread. But it's not so good because it still leaves it sharp and easily damaged. Then of course there are all sorts of different head shapes. This is the standard hex head, which is good, and you get a good grip on it with a spanner. But it only goes down to a certain size. This is the smallest. This is 5mm thread with an 8mm head on it, and that's about as small as you commonly get them. Below that, the bolts tend to have posi heads or flat heads. Then of course there are countersunk versions of all these things. For smaller sizes it's usually posi. For larger sizes it's often like a hexagonal key, like for an Allen key. Then of course there are Torx heads, which have become very common on cars and white goods, good with automatic screwdrivers, I guess. The only trouble I have with those is that the drivers don't seem to last very long. It's easy to mash them up. Then of course there are a lot of older head designs, well, just a basic flat head, or I don't know, that's called a roofing bolt, a coach screw, that's got a square underneath that grips the material. And then there are a lot of bolts like set screws that are designed for Allen keys. I use quite a lot of these. I find them good for getting them in awkward places, and you can get a good grip on them as well. So this is the cap head, this is the countersunk version, and this one's called a button head. They kind of look rather neat, the button heads. And then there are some more specialist ones like a collar bolt. So this is a precise 12mm diameter, so you can put a bearing on it, which I find very useful. I particularly use tiny ones like this. This is a 5mm collar bolt with a roller bearing. It's very compact and hard wearing. Then for every size of bolt there's also a stainless steel version, and I keep both. I have to use the stainless steel for things outdoors on the pier, obviously. I used to love the stainless because they're so shiny and of course never rust, but I've rather gone off them. The steel isn't quite as good for nuts and bolts, really. There's a compromise because they're stainless. It's somehow not quite so hard. It's a little bit softer and more sticky, so nuts are much more likely to jam up with stainless than they are with the ordinary mild steel. So if you've chosen your bolt and got the right head, the next thing is how tight to do it up. Well, I have to admit I don't even possess a torque wrench. It's essential if you're working on a car engine or something, but for my sort of things I just tighten them up till it sort of feels about right. You get to know after a while. And what really helps is that big nuts and bolts, it comes with a big spanner. So you've got much more leverage on a big bolt than you do on a little bolt. This is my little 5mm thread, 8mm spanner, and this comes with a dinky little spanner that's that long. So the difference is quite dramatic, but it means you sort of automatically get a much bigger leverage on the big bolts than you do on the little ones. I mean, mainly the point is that you don't want them to come undone, and often the problem with coming undone is vibration. You can buy special washers, spring washers. This is a common sort. It kind of digs into the head and into the metal to stop it working loose. For smaller sizes, you get these ones with just lots of serrated edges that dig in. Bicycles have nuts. A similar sort of idea. These shapes help to stop it spinning loose. Actually, just simple washers help because it just helps you to tighten up the nut more evenly. It reduces the friction, so you can get a better tension on it. Another way of preventing vibration running things loose is a nylock nut. So these are nuts which have a little ring of nylon crimped in, and these grip the thread to some extent, so it gets a lot stiffer when it's gripping the nylon, and that makes it less likely to come undone. And of course there's Loctite, which I've mentioned before. It comes in different strengths. You just drip it on the joint between the bolt and the nut, and I think it works very well. Now this one's clever. You can actually drip it on a nut and bolt that's already done up, and it seeps in to the crack by capillary action.
There's a floor. There's a ceiling on the floor. That's the ceiling.
Well, it's easy to make a mistake though. This is a project I did with my friend Andy. It's a version of a Victorian fairground ride called the Haunted Swing. We gutted an old caravan and stuffed a shaft through the middle with bearings on either end. We then later cut the shaft and put a long bench seat in, which seats about 9 people. We took it round to fairs for several years without any problems, but then it went to Banks's Dismaland and was used intensively for a couple of months. And we got a call in the middle saying that it was making loud banging noises. So I rushed down there and I found that all these bolts had worked loose. And this is just a sort of scale model I've made to show you. It's a similar sort of bearing. Well, these bearings, they're called self-aligning because they have this curved outer, which is very handy. Because I don't think caravan were particularly true. But we thought once it was in place, it would just stay in the same position, which was fortunate because the bearings we had, this was very, very stiff, this self-aligning mechanism. But I think because it was stiff and we probably hadn't managed to realign the shafts at each end absolutely perfectly, it was going in jumps because it was stiff. And it was this sort of tapping that eventually forced the bolts loose. So sometimes now where it's really important that nuts don't come undone, like on truck wheels, you get these indicators or telltales, I call them sometimes, which are lined up so that they point at each other. Obviously the point of these is that you can instantly see if one of them has changed position. I used to be quite casual about it and often just used the drill bit to drill the countersunk. But if the angle's not quite right, you can get into trouble. The bolt is only in contact at the root of the head, not over the whole area. Well, a friend of mine did. He built this sculpture thing with a huge turntable, about 20 foot in the air, and with an overhanging arm. And the people who'd fabricated it had fixed it with 18 12mm countersunk bolts, but they'd use the drill bit to countersunk them. It's very tempting because it's so quick doing it with a drill bit, but it's only making contact down the bottom. Now the problem with this is that it can then very quickly wear. I'm now going to tighten this countersink bolt, the badly drilled one, into a lump of metal. Get it as tight as I can. Now, this is the test. You can see it didn't take long to get it to be quite wobbly. So once it's wobbly, then there's a sort of tapping load on the bolts, and it will, after a while, it'll break by fatigue failure. And of course in that turntable, when one breaks, puts more load on the rest, and so it's like a sort of daisy chain. No. By the time it was noticed, 10 of the 18 bolts had already completely sheared off. One other thing about countersinking: I used to have great trouble getting countersunk bolts, drilling the countersunk bolts so they were completely flush with the metal. And only comparatively recently realised that I wasn't making full use of the little sets of countersunk bits. The key is to choose the one that's closest to the diameter of the countersunk head, because then when it reaches the parallel bit, you can sort of see it as it drills. When you get to this point, there's a little bit of flashing, just very, very slight raised edge that appears when you get to the parallel bit. That's pretty perfect. That's satisfying. But of course it's important not to over tighten bolts because you can strip the thread, and they can also strip just by overuse. So with a lot of these machines, when they're new particularly, I keep having to take the covers off the frame to tinker with them. And so I'll just take this one off like this. They're screwed on. But I had to unscrew them so many times that they completely stripped the thread, because the metal's pretty thin. It's only about 1.5mm wall thickness, and so the answer to this are these little things called clinch nuts. What they're sort of almost like a pop rivet. So they go into a sort of pop rivet gun, I've already drilled a hole you have to pull really hard. Oh, yeah, it's going now. But you can sort of see down the tube maybe how it's pulled the metal of the nut against the tube. So it's a really good fit, a tight fit. And now there's probably 4 mil thickness of thread through there, and they'll last forever. If you do need to restore a thread to its original size, there are these ingenious sets of thread restorers. I've only actually ever used one twice, I think, but they were lovely things, so I thought I couldn't resist showing you them. So there's my stripped thread, a stripped 8mm thread. The first thing is to drill out the hole a bit. In this case it's to 8.5mm. So the next thing is that the sets have a special tap in. Now this has the pitch of an 8mm, but it's a bigger diameter. So we now run this through the hole. We'll just get a bit of WD-40 to put in it. So that's our oversized tapped hole. Now we use this tool, and really it's these little inserts that are the heart of the system, and you just wind this in. That's right. I think that's going now. Get it a bit below the surface is what they say. Yeah, there we go. And that now, the inside of that is a perfect 8mm thread. A perfect fit. To wind them in, they have this flat bit at the end, and a wonderfully crude way of removing the flat bit is just a punch, and you just smack it with a hammer. And then you're left just with a perfectly threaded hole. Very clever. Then of course there are wood screws. They've actually been around for a surprisingly long time. They were actually made by hand, filed individually, since the 15th century on posh bits of furniture. And there's also a rather cruder version made from nails. So most nails had a square section because they were forged, and they could be twisted like that. And I've read that it was gunsmiths who found that it was useful to be able to remove the lock, the flint lock, the metal part, from the wooden gun stock for repair, and so they put a slot in the top of these nails to give it a twist to start it coming loose. But of course it wasn't until the advent of automatic lathes in the 19th century that mass production became a possibility. In Britain this was started by a Mr. Nettlefold, and the shape of the screw is the sort of classic wood screw that remained unchanged until comparatively recently. Nettlefold set up shop just round the corner from Novelty Automation in 1819. But of course today wood screws are amazing. With the modern production machinery, the things you can do are extraordinary, really. I've got this bit here which can sort of grip the screw. Then further down you can see the actual thread is serrated, and when you get near the tip there's this little V cut out. I think that's to help it drive its way into the wood without drilling a pilot hole first. I have to admit though that most of the time I just use cheap carcass screws. They work just fine for fixing plywood to wooden frames and that sort of thing. Sometimes to get them started, or it's quicker, I find to knock them a bit of the way in with a hammer before actually screwing them. And that won't come undone. Then there are self-tapping screws. These are a sort of hybrid, a sort of half and half between a wood screw and a bolt. If you look at one closely, they're very different shape from either. They've got this wide flat bottom and then these very small pointy threads. The angle of the thread is probably only about 30 degrees, and then this one's got an ordinary posy head. But these can go through much harder material than wood, so they're good for fixing thin aluminium and even steel. And a surprisingly strong joint. So this is a latest machine, Supercycle, cycling game obviously, but also includes a bit of doping. Anyway, the screw threads that are interesting here are the self-tapping screws, and I find it particularly useful for polycarbonate, fixing bits of polycarbonate together. Like on these chain guards, you can see the rows of little self-tappers. And polycarbonate's a lot stronger than perspex, so it's better for things like that. So the thing to remember is because the plastic is quite strong, you don't want to drill a hole that's too much smaller than the outside diameter of the screw. And so I'm going to drill a 2.5mm hole in the polycarbonate here. Oops. Well, that's one. Oops. And just two of those little screws has an enormous amount of strength. So the threads in my machine tools, and also those ones in G-clamps, are a different shape. They're sometimes called castle threads, I guess, because they look a little bit like the battlements. And the point of this shape is that it can transmit a lot of force, so you can clamp something up hard. But I find them very useful for converting rotary motion into linear motion. And I've used this on one or two machines, particularly on divorce, for opening and closing the house in the middle. There's quite a lot of play in these nuts, so it's not entirely precise. Precision screw threads are another subject. The most precision screw I have in the workshop is in my micrometer. Extraordinary thing is it's accurate to 0.001 millimeters. That's 10 times more accurate than my calipers that I use all the time. I don't often use this. It's more accurate than I can cope with in a way. But making a precision screw like this is tricky because Once you've cut the screw, you have to harden the thread, and to do that you have to heat treat it, and that distorts the metal. So after the heat treatment, it has to be finally ground to the final shape in a precision grinding machine. And that's how all precision screws are made. So the precision version of the Acme thread is the ball screw. And these are beautiful things. I've never used one in one of my machines because they always used to be so expensive. But you can now get real bargains from China. I just got this, and it was £17. I'm not quite sure in one of my machines where I would need this precision, but I'm tempted now. The nut itself is amazing. Inside there are lots of ball bearings that run round in a circular track. This is the biggest clock, or biggest clock dial anyway, that I've ever made. Another project with my friend Andy. And just fixing it to the building was quite epic. But fortunately we had Paul, who was an experienced offshore rigger and welder, who took control. And he arrived with a bigger version of this. It's a round thing that tapered to a point. And we weren't quite sure what he was going to use it for. But once he was up in the air, it was obvious. If you've got a huge frame that's suspended by the crane, it's very difficult to line up the holes. So what you do, you stuff your podger through a hole in the frame that's moving about, and then you try and get the other end in the bracket in the building. And then as the crane slowly lowers, you can sort of lever it to make the holes line up. And then, of course, you can drop the bolt in, and the rest is quite straightforward. So whenever you see somebody high up on a construction site putting steel together, they're bound to have a podger. On a small scale, I find it useful to grind the ends of bolts to point on my limiter. So if I've ground the head on the bolt, it's much easier to fit a panel to a metal frame, because I just push it over and I can feel now that the tip has gone in, and then wiggle it a bit, and now the thread has started. Much easier than if it's flat on the end of the bolt. So my other thing that I've learned about making frames, like the frames on my machines, they're mostly welded, but there are some bolted joints to take parts out for maintenance and to get at other parts that are hidden. And it may sound counterintuitive, but I always do the bolted joints before the welded ones. I think perhaps the best example of this, and certainly the biggest, is on the clock I made for the Exploratorium at San Francisco, which had to fit around a column. So when I arrived on site, the whole frame had to be split into two halves and then rebolted together. So just as I was saying, I started by the bolted joints of the frame. So this is half a side piece that I'm bolting to a short joining piece. And I'm now welding the other side of the short joining piece to the other half of the side piece, if that makes sense. So this is our finished horizontal side piece for the cloth. We actually made 16 of them. And this is how we started on the frame. And then the next day we went outside and welded everything else together. So actually I never undid these bolts until I got to San Francisco just the night before we assembled it. And I was nervous whether they would go back together. But they did all fit perfectly. It was very, very satisfying. So yeah, do the bolted joints before the welding.
for it to.
I thought I'd end by talking a bit about extracting rusty old bolts, a frustrating business. So if you've got a bolt like this is a pan posi head, and the head is completely mashed, it happens very easily, you're not going to unscrew that. Well, conventional wisdom is a bit of WD-40 or heat it up, but there are lots of situations where you can't heat it up, and WD-40 often doesn't do the trick. So a couple of things that I've found useful. First is my mole grips. So just to grip the bolt round the head, you've got to get it exactly right, the tension, so it's gripping the head really firmly. And then once you've got it right, you can snap them shut, and then you can... I've got that one to turn. I wasn't sure if I would actually, but I'll tighten it up again because I'll show you the other technique that I've found useful, and that is simply to use an angle grinder to turn the head back into a flat-headed screw. And then I quite often hammer the screwdriver in so it's got good contact. And then also another thing, I quite often then use my mole grips again just to grip round the screwdriver to give myself better leverage. Well, that was a bit loose already, I think, so it wasn't a good test really, but I have found that very useful for these pan posies. But of course things get more difficult for larger bolts. So then there are these things called screw extractors. The idea is that you drill, made of hard steel, you drill that bit in up to there, then turn it over, and then you force this one in, the spiral going down into what you've drilled. This is a new bolt. I just tightened it as much as I could. Seems to need a pilot hole first. Then it's a bit weird, you have to drill the thing in backwards, then flip it over, and the taper screw thing does grip extraordinarily well. That part of it's good. Go. Not the biggest success. Maybe other situations it would work. The thing that I've found had much more success with unconventional technique is welding to the head of the bolt or the remains of the stud. So a nice blob of weld not only gives you a good connection to the head, but it also provides quite a lot of heat, which can sometimes shake the thing loose. And then of course you've got a nice big lever arm to try and force the nut loose. Let's see if I can tap it loose. Yeah, I think that's going to come quite easily now. That was easier than sometimes because the thread wasn't in too bad shape. Well, that's the end of this episode. Turned out to be rather a mammoth one, and there's lots more I could have put in. But I hope you found something useful from it. It was fun to make this one.